Hello, hi everyone. Welcome to the Spectral Geometry in the Clouds. This week we have the pleasure of having Ilaria Fragalà from Politcenico di Milano, and she will speak about Riesz inequality for polygons, symmetry, and symmetry breaking. The stage is yours, Ilaria.
Thank you very much, and thank you to all the organizers of this seminar for inviting me. It's a pleasure to give this talk in the class. And the topics of this talk are a recent joint work in collaboration with Beniamin Bogosel from Institut Politcenico di Paris and Dorin Bucur from the University of Mont Blanc, and are about this Riesz inequality for polygons. So the problem I'm going to discuss is the following. We want to investigate the validity of a polygonal counterpart of the inequality due to Riesz, which states the following. So take any non-negative, non-increasing radial kernel H, locally integrable in Rd. So for instance, H may be a Gaussian function, but H does not need to be continuous. So for instance, it can be the characteristic function of a ball, which is equal to 1 in a ball centered at the origin and 0 outside. Then the inequality by Riesz tells that for every measurable set omega in Rd, the double integral over omega times omega of this kernel H computed at x minus y dx dy is always less than or equal to the analog integral, in which the integration domain omega times omega is replaced by omega star times omega star, where omega star denotes the ball centered at the origin with the same Lebesgue measure as omega. So this is a classical rearrangement inequality dating back to 1932. So the question I want to discuss is what happens when we are in dimension d equal 2. So all my talk will be in dimension 2, and omega belongs to the family Pn of polygons with a fixed number n of sides. And of course, we fix also the area. For definiteness, let me take area equal to pi. So in particular, the question is the following: is the analog inequality true when I replace in the right-hand side the ball, omega star, by the regular polygon of n sides and area pi? So I'm going to try to give a quick historical introduction to the problem, then tell you what is the state of the art and our results. If I have time, I would also like to discuss some of the questions and some related numerical results. So to start, let me say that the problem of studying polygonal versions of isoperimetric inequalities having balls as optimal domain is a very, very natural question. And in fact, it has been studied both in the classical geometric setting for the classical isoperimetric inequality proved by De Giorgi, which states that balls minimize perimeter under a volume constraint. And it has been studied also in isoperimetric inequalities in mathematical physics, such as the classical Faber-Tran and Saint-Benoît inequalities, which state respectively that balls minimize the first Dirichlet Laplacian eigenvalue lambda 1 and maximize torsion under a constraint on volume. And when dealing with polygons, it happens that the level of difficulty is drastically different when passing from the geometric setting of perimeter to the, say, physical setting of lambda 1. In fact, the fact that the regular polygon minimizes perimeter under a fixed area and number of sides is a well-known fact. Several elementary proofs can be given, and they can be found in several textbooks in convex geometry. On the other hand, dealing with the physical cases of lambda 1 or torsion, the regular polygon is known to be optimal only when n equal to 3 and 4, that is to say for triangles and quadrilaterals. But the question is open for n larger than or equal to 5, that is from pentagons on. And the fact that these inequalities are true for a number of sites larger than or equal to 5 is a famous conjecture due to Polya and Zigo. It can be found in a monograph by Polya and Zigo about isoperimetric inequalities in mathematical physics. But actually, the conjecture can already be found in a paper by Polya alone, which dates back some years before, where Polya writes this sentence: the difficulty that we face when attempting the extension to pentagons can make us realize that our theorems on symmetrization are far from being trivial. In fact, they are so far from being trivial that the conjecture is still open after more than 75 years. And essentially, not so much progress has been done since then. Let me mention that meanwhile, the optimality of the regular and-on has been proved for other variational functionals other than lambda-1 and torsion, which are still variational but are a little bit easier because somehow they are more geometric. This is the case of logarithmic capacity, for which the regular polygon is known to be optimal by a paper by Solin and Zalgaller, and also we proved the result for the Chigger constant with Dorin Bucur in 2016. But why is the physical case so more difficult than the geometric case? Well, essentially, the main difficulties in a very naive way can be described as follows, and these are also the same difficulties which arise when studying Riesz polygonal inequalities. The first difference between the geometric and physical case is that in the geometric case, you have an important a priori information on an optimal polygon, because you know immediately that an optimal polygon must be convex. Otherwise, you convexify, you decrease perimeter and increase the area. So you know a priori that an optimal polygon is convex. While for lambda-1, this is not known. It is open to establish whether for Polya and Zigo problem, an optimal polygon is convex. And even worse, for lambda-1, an optimal polygon might be an object of this type that I call a generalized polygon, because minimizing sequences of polygons in Hausdorff distance may converge to objects like this, which have self-intersections in their boundary, which may be points like here, or line segments like here, here, and here. And so while for polygons, once you know that your optimal polygon is convex, and in fact, it is also easy to see that it must be also circumscribed to a disk, you may use explicit formulas for perimeter and for the area, so that you can easily prove that an optimal polygon must have all the sides equal and all the angles, inner angles equal. While for lambda-1, there are no explicit formulas for the energy of polygons, not even for regular polygons. And so since you don't have any a priori information on optimal polygon and no explicit formula for the energy of polygons, you are forced to use some kind of symmetrization technique. And of course, the symmetrization technique that you would like to exploit is a spiral symmetrization, which is a very well-known tool in shear optimization to prove symmetry results. You know, you fix a line in dimension 2, and for every set, you replace every slice of the set in direction orthogonal to that line by line segments which are centered on your line. This way, you, for sets, you decrease perimeter and you leave unchanged the area. While for functions, you preserve the LP norm and you decrease the LP norm of the gradient. So in particular, lambda-1 decreases. And here is the point where the difference between the cases n equal 3 and 4, triangles and quadrilateral, or n bigger than or equal to 5, this difference here shows up, because for triangles and quadrilaterals, standard symmetrization works fine. Because if you start from a given triangle, you can make a sequence of standard symmetrizations with respect to the mediator of a side and make it converge to an equilateral triangle. In a similar way for quadrilaterals, in a finite number of standard symmetrization, you can transform it into a rectangle. But in general, for instance, this is represented here in case of a pentagon. In general, when you take the standard symmetrization of a polygon, you may increase the number of sides. You can see here a pentagon, which after a standard symmetrization becomes a hexagon. This photo is taken from the book by Antoine Enrault about exponential problem for eigenvalues of elliptic operators. In other terms, the constraint of the number of sides is not closed under standard symmetrization. And this is the great difference between the cases n equal 3 or 4 and n larger than or equal to 5. And these difficulties which arise in case of Politcenico conjecture arise in the same way also when studying polygonal Ritz type inequalities. There is a small advantage in studying Ritz type inequalities, and the small advantage is the fact that the problem is purely geometrical. You don't have any PD to deal with. And in fact, I like to see Ritz inequality as a kind of bridge between the easy case, which is the geometric case of the isoperimetric inequality, and the difficult case of physical isoperimetric inequalities. And I say it's a bridge also because it is related to both of them. Ritz inequality is related to both the isoperimetric inequality and to Politcenico conjecture. So let me tell you briefly what are these relationships. Well, the relation between polygonal Ritz and polygonal isoperimetric inequality is easily seen if you take into account that this is the Ritz energy that we want to maximize. I denote it by JH. So now, if one looks at this integral here, h at x minus y, as a kind of interaction density between particles x in omega and particles y in the complement of omega, one may do the following. One may observe that this Ritz energy agrees up to a translation and a change of sign with this functional pH, in which one replaces one of the two integrals over omega by an integral over the complement of omega. And so this functional, which agrees with the Ritz energy up to a translation and change of sign, can be viewed as a kind of nonlocal perimeter. This is a notion of nonlocal perimeter, which was first introduced by Bucur, Riesz, and Mironescu 20 years ago, more or less. And then this notion of nonlocal perimeter has been widely developed, in particular in case of the fractional kernel, in papers by Caffarelli, Suganidis, Caffarelli, Lopez, Sabin, and many more. And recently, there is also an entire monograph by Mason, Rossi, and Toledo, which is devoted to study the case of bounded integrable kernels. And so if one looks at our problem from this perspective, when we want to maximize the Ritz energy over the class of polygons with a fixed number of sides, since these two functionals differ just by translation and change of sign, what we are doing, we are minimizing a nonlocal perimeter over the class of polygons with the given number of sides and given area. So in other words, what we are studying is a nonlocal version of the classical polygonal isoperimetric inequality. So this is the relation with the geometric isoperimetric inequality. What is instead the relation with the Politcenico conjecture, so with the physical case? Well, to see this relation, one has to notice that both lambda 1 and torsion admit a probabilistic reformulation, which is expressed by these formulas, and this probabilistic reformulation allows us to write lambda 1 and torsion in terms of the probability that a Brownian motion starting at a point x0 of omega has not left omega by time t. So this probability appeared here in these formulas, and in turn, this probability can be written as a limit when m tends to plus infinity of a m pool of integrals. Here you have m integrals, and what you integrate is a product of Gaussian functions. So heuristically, the presence here of the Gaussian functions or heat kernel is due to the fact that the transition probabilities in the stochastic process are the fundamental solution of the heat equation. While still heuristically, the fact that here you have a multiple integral is due to the fact that the Brownian motions are continuous in time, so it is enough to check that very often your particle remains in omega. Anyhow, starting from these formulas, you can reprove, you can recast the classical Faber-Tran and Saint-Bernard inequalities with bonds as optimal domains by using a rearrangement inequality for multiple integrals due to Braskamp, Lieb, and Luttinger, which states that for every m, this multiple integral is always less than or equal to the analog multiple integral in which you replace m copies of omega by m copies of a ball. And so, in this perspective, if one want to prove Politcenico conjecture, a possible approach would be to prove a polygonal version of this Braskamp-Luttinger inequality. Of course, this is very difficult because this should be done for every number m of integrals. And of course, the first cases one wishes to look at are the cases of small m. So in particular, when you have just two integrals, a double integral, you are dealing essentially with our problem, with polygonal reeds. But this way we realize that there is another case which is even simpler, but not trivial, which is the case when you have just one integral. And in that case, proving a polygonal version of Braskamp-Lieb-Lüttinger inequality corresponds to prove a polygonal version of another classical rearrangement inequality, which is the rearrangement inequality by Hardy and Littlewood. And so let me tell you what is known in the literature about polygonal versions of these two rearrangement inequalities. So the polygonal Hardy-Littlewood inequality tells that this quantity for every admissible kernel H is less than or equal to the same quantity when you replace omega by a ball. When omega is a polygon, the fact that the same inequality holds true with the regular polygon here in the right-hand side is known to be true for every n for the distance function h, and with the restriction that the admissible polygons are convex. This result can be found in the paper by Morgan and Bolton about the hexagonal economic regions. While concerning polygonal reeds, well, up to date, the unique polygonal reeds inequalities known in the literature concern the cases n=3 and n=4. That is to say, triangles and quadrilaterals. And the reasons are essentially the same as for Politcenico conjecture. For these values of m, it is known that the regular triangle and the square are the unique maximizers. This is proved essentially by standardization, even though not explicitly stated in the paper by Braskamp-Lieb and Lüttinger. And for n=3 and 4, it is also known that the regular triangle and the square are the unique critical polygons. This is a more recent result, a nice result by Donacini, Cristofori, and Topaloglu. And what does it mean that a domain is critical for its energy under volume constraint? Well, it means that it satisfies first-order optimality conditions. That is to say that the shape derivative of its energy is proportional to the shape derivative of the constraint, so of the volume. And this must be true for every admissible perturbation. So this stationarity condition, this criticality condition, can also be written more explicitly, taking into account that the Ritz energy, as I've said, is up to a translation the opposite of perimeter. And so in the same way as the first variation of the classical perimeter is expressed by the mean curvature, the first variation of the non-local perimeter is expressed by this functional capital H omega, which is a sort of non-local mean curvature. And recently, sets with this constant non-local mean curvature have been studied in the literature. In particular, there are these two independent papers, 2018, by Ciraulo, Figali, Maginovaga, and Cabré, Paul, Sora Morales, and Webb, where it is proved that balls are the unique smooth sets with constant mean curvature. And in the fractional case, the problem makes sense only for smooth sets because the kernel is singular. While in these two recent works with Dorin, Bucur, we studied the critical sets with the constant non-local mean curvature. In the first paper, when H is the characteristic function of a ball, and in the second case, when H is an arbitrary locally integrable kernel. And we found that these sets are either balls or multiple union of balls according to the geometry of the kernel. But now we want to deal with polygons. So when dealing with polygons, if one wants to study critical polygons, of course, one is forced to use domain perturbations which preserve the number of sides. And domain perturbations which preserve the number of sides are essentially originated just by a family of 2n elementary movements, 2n because there are 2 for each of the n sides of my polygon. And these two movements for a fixed side amount either to rotate the side with respect to its midpoint, like here, or to move my side in a parallel way to itself. And for these two movements, the stationarity condition for its energy are written here. So if you denote by AI and AI plus 1, the two endpoints of the side I'm moving, and by mi, the midpoint, the first order stationarity condition with respect to this movement corresponds to ask that the integral over the first half of the side of the mean curvature times the distance to the midpoint must be equal to the integral of the same quantity over the second half of my side. While the stationarity condition with respect to this movement corresponds to ask that the integral over this side of the mean curvature is proportional to the length of the side, through a constant which of course must be independent from the side you are moving. So in their paper, Beniamin, Christopher, and Topologlu were able to prove that for triangles, this system is satisfied if and only if the triangle is the equilateral triangle. And same result also for quadrilaterals. For triangles, they could prove the results by using our reflection technique that we introduced in a paper with Velichkov to prove the analog result for lambda 1. But that technique holds just for triangles. For quadrilaterals, they were able to give a very nice new proof by using slices and extending the results to quadrilaterals. And now let me start discussing our results. So all the results I'm going to present are contained in this paper with Beniamin, Bogosel, and Bucur, which is posted on the archive. And so our first result states that the polygonal Hardy-Littlewood inequality with the regular polygon as optimal domain is always true, where always means for any kernel, not only with the distance function as in the paper by Morgan and Bolton, but means especially for arbitrary polygons with no need to impose convexity. And in fact, the proof is in two parts, and the most delicate part of the proof consists in showing that an optimal polygon exists in the class of simple polygons. Because in principle, when you take a maximizing sequence for this energy, it might converge to a generalized polygon having self-intersections in its boundary. And if the optimal polygon is a generalized one which has a self-intersection in the boundary, you are not able to move the sides and exploit first-order optimality conditions to see that the optimal polygon must be the regular one. By contrast, if you know that an optimal polygon is a classical polygon, it is not difficult to show by exploiting the optimality condition that the optimal polygon must be the regular one. And so the most delicate part is to show that an optimal polygon exists in the class of simple polygons. And actually what we prove is that an optimal polygon exists in the class of star-shaped polygons. To do that, we first reduce ourselves to consider the case when the kernel is the characteristic function of a ball. By approximation, this can be done in a standard way. And so look at this function that we want to maximize. When h is the characteristic function of a ball, what you want to maximize the integral over omega of the characteristic function of Br. In other terms, what you want to maximize is the intersection between omega and a polygon. So this is a purely geometrical maximum overlap problem that we found already mentioned in an old paper by Fejes Top. And so we needed to set up an ad hoc global construction for this maximum overlap problem to prove that it admits a star-shaped solution. So essentially what you want to do, given a polygon, you want to construct another polygon which is star-shaped, has the same number of sides, and has a larger intersection with the ball. And to do that, let me show you just a picture to have a very, very quick idea. So you're given an n-gon, you want to construct another n-gon, so very important, with the same number of sides. This new polygon must be star-shaped and must have the following properties. Inside the ball, the new polygon omega prime must be larger than the original polygon, so to increase the energy, while outside the polygon, your omega prime, you want it to be smaller than omega. If you construct omega prime with these two properties, then a suitable scaling does the job. So how to enlarge the polygon inside the ball and make it smaller outside? Well, look just at the picture in the first row. So on the left, you see the initial polygon in blue. And on the right, you see in dotted line the original polygon, and in blue the new one, which is a star-shaped. So what you do to construct this new polygon in blue, so you look at the intersections of the original polygon with the boundary of the ball. And we start by considering this special configuration in which the original polygon has this property. All vertices are outside, and each side is first out, then in, and then again out. So we first examine this simpler case. This is a kind of zigzag configuration. So if my polygon has this shape, the intersection of my polygon with the ball is given by a number of arcs of circle, and these arcs of circle are exactly as many as the number of sides as omega. So we look at these arcs of circles, say pi, qi, and to construct the new polygon, we join qi with the first endpoint of the subsequent arc of circle. So we join qi with pi plus 1, and here as well, we join qi minus 1 to pi. And we construct this new polygon in blue, and it is not difficult that it does the job, because it contains omega inside, and it is contained into omega outside. In the general case, the construction is more delicate. I don't want to discuss it here because you may have vertices inside. So you have to consider the convex envelope here. And also outside, the situation is more complicated. So the construction must be done by fixing a point inside and considering a family of rays which emanates from this point. Anyhow, the conclusion is that Hardy-Littlewood is always true. And the interest in this Hardy-Littlewood inequality is also the fact that it can be used to prove some new result for the Riesz type inequality for a particular kernel. So let me explain why. Well, to investigate the polygonal Riesz inequality, we started from a special case, and the special case is the case when the kernel H is the hit kernel, which has, of course, a special importance also in view of its connection with the Politcenico conjecture that I have discussed before. And so if you consider this kernel H, the corresponding double integral is the so-called heat content of omega, because it represents the quantity of omega, of the quantity of heat, which is kept by omega if you heat omega at time 0 with the constant temperature, and you keep its boundary at temperature 0. And if we want to investigate the validity of Riesz inequality for this special kernel, we can heuristically look at what happens in the limit when t tends to 0 and in the limit when t tends to plus infinity. So this quantity, the heat content, has been studied in the literature in many papers, in particular in the case of polygons by Vandenberg and co-authors. I apologize because for sure here the list of references is not complete. Anyhow, it is known that this is the asymptotic of q omega of t in the limit when t tends to 0. So the zero order term is the measure of omega. So for us, it is a constraint, it is constant. Well, if we want to understand what happens, we have to look at the coefficient of the subsequent term. And look here in the coefficient, we have minus the perimeter. So the perimeter is minimal at the regular and gone, which means that heuristically for t tending to 0, the Riesz type inequality will be true because this quantity will be less than or equal to the same quantity for the regular and gone. And similarly, in the limit when t tends to plus infinity, again, you get a constant term at the first order, while at the subsequent order, you find as a coefficient, by using the asymptotic expansion of the exponential function, you find as a coefficient this double integral, where you integrate the square of the norm of x minus y. And this fact drew our attention to the following question: is Riesz inequality true for power 2 of the norm? Of course, power 2 is increasing. It is not a decreasing kernel. In fact, here we have a minus sign. So if you want to investigate Riesz inequality for power 2, of course, we have to revert the sign of inequality. But is Riesz inequality true for power 2 with the sign reversed? And the answer is yes. The answer is yes. For power 2, and actually also for power 4, the regular polygon is optimal for Riesz inequality for every n, not only for triangles and quadrilaterals, but also for pentagons and polygons with a fixed number of sides. So to my knowledge, this is the first polygonal version of Riesz inequality, which holds true for an arbitrary number of sides. And the truth is extremely simple. Look at what happens for power 2. For power 2, you can expand Riesz energy simply by writing explicitly what this squared norm is. And when you compute here the integral of the first two terms, since here y doesn't appear, when integrating dy, you have just a constant, this pi, which is the measure of omega. Same thing when you integrate the third and fourth terms. While the integral of the fifth and sixth terms are simply the square of the coordinates of the barycenter omega, which after translation, we may assume to be equal to 0. And so, if we assume that these two last integrals are 0, we have only to deal with this integral, which, as you can see, is a single integral, and it is precisely an integral of Hardy-Littlewood type. So, by using the optimality of the regular n-gon in Hardy-Littlewood, we get the result for power 2. Of course, it is a result which holds true for every n, as I've said, but sure that the kernel is a very specific one. It is power 2. We are able to extend the result to power 4 by the same strategy. You develop power 4, you get some more terms, but we are able to handle these terms by using the optimality of the regular polygon under stretching, and we end up also with the result for power 4. But already for power 6, when you expand power 6, there are many more terms, and we were not able to handle all these terms. So for theory, we were not able to prove the result for all n even, and it is also clear that this strategy cannot work for n odd, nor it cannot work for instance, for non-integer powers. So at this point, we decided to look at another family of kernels, which are still somehow simpler as powers are, but at the same time, they are meaningful because they can be used to approximate any other kernel. And this family of kernels are characteristic kernels. So as we did with Hardy-Littlewood, we decided to look what happens when h is the characteristic function of a ball. And when h is the characteristic function of a ball, let me denote by JR the corresponding Riesz energy, we could prove that symmetry holds in the regime of a small radius. In other words, for every n, so for every number of sides, there exists a critical threshold, R prime, which only depends on the number of sides, such that if you take R smaller than this critical threshold, your Riesz energy is less than or equal to the Riesz energy of a ball. Or if you prefer to look at the nonlocal perimeter, the nonlocal perimeter associated with a characteristic kernel is minimized by the regular n-gon, provided the radius of the ball is sufficiently small. Okay, the proof of this result is rather involved, so I don't want to discuss it here. Let me just say that we first proved the result for convex polygons. And for convex polygons, the proof is by contradiction. We assume that an optimal convex polygon is not the regular one, and by using an asymptotic expansion of the nonlocal perimeter in powers of R, in which the classical perimeter appears in the leading term, we can show that the optimal polygon among convex polygon must be close to the regular polygon. And then we obtain a contradiction because this tells us that close to the regular polygon, there would be a critical polygon. And we know that this is not possible because we have an independent symmetry result for critical polygons that I'm going to show you in the next slide. So this way we deal with convex polygons. In case of arbitrary polygons, the proof is more involved. We have to deal with these possibly generalized polygons with self-intersection in the boundary. But we are able to do that by using triangulation and making local estimates near the sides of the generalized polygons where there is no accumulation of vertices. But let me tell you what is this symmetry result for critical polygons that we use to get symmetry in case of convex polygons. So this is a symmetry result for critical polygons, which somehow is related to the result by Bonacini, Cristofori, and Topologlu that I mentioned before. So let me take a critical polygon for Riesz inequality, when H is the characteristic kernel. So remember, this means that my polygon satisfies the system of 2n equation that I get when I move one side, either this way or by parallel movement. And we can prove that this critical polygon is necessarily a regular n polygon, provided the radius is sufficiently small. And let me explain you why we need the smallness condition on the radius and which kind of smallness condition on the radius do we need. So this smallness condition on the radius comes from the method of proof, which is again the reflection method I mentioned before. In fact, the proof is by contradiction. Let's look first at what happens for triangles. Well, for triangles, the smallness condition on the radius is not needed. For triangle, the result works for an arbitrary radius. Let me tell you why. So assume that there are two different angles in my triangle. This angle is larger than this one. So I take the side which is adjacent to the two angles. I take its mediator and I write the optimality condition which corresponds to rotate this side around its midpoint. Now, if I look at two balls which are centered at symmetric points with respect to the mediator of this side, inside these two balls which are represented here, there cannot be the same mass. That is to say that the intersection of my triangle with this left ball is necessarily strictly smaller than the intersection of my triangle with this right ball. And this is due to the fact, you can see it very clearly, I think, from this picture. This is due to the fact that the reflected triangle is contained inside. Why? Because this angle is smaller than this one. Right? But when I look at arbitrary polygons, the fact that this angle here is larger than this one does not imply anymore that the reflected polygon is contained inside, right? Because you can see it, as it happens here, the reflected polygon goes outside, though this angle is smaller than this one. And so the smallest condition that we need here to get this symmetry result for critical polygon is the following. We have to impose that for every point x in the boundary, if you consider the ball of radius r centered at this boundary point, its intersection with the boundary of my polygon must be contained into a pair of consecutive sides. By this way, we are sure that here the inclusion is satisfied, as it happens for triangles near for all points of this side, when r is sufficiently small. Now, for a long time, we thought that this condition, this smallness condition of the radius, was somehow a drawback of our method, of our reflection method. And in fact, we thought that the result was true. And I have to say that also in their paper, Bonacini, Cristofori, and Topologlu, even though they deal with different kernels which satisfy some smoothness condition, they conjecture that the inequality is true for arbitrary n. But then we had a big surprise, and the big surprise is that when you take as a kernel the characteristic function of a ball with a sufficiently large radius, we have symmetry breaking. That is to say, the regular polygon is not optimal for Riesz type inequality. And this phenomenon occurs for every number of sides even larger than or equal to 6. More precisely, for every such n, there exists another threshold, r2, which again depends only on the number of sides, such that for r, which is above this threshold and smaller than the diameter of the regular n-gon, for every r in this range, the regular polygon is not optimal, doesn't maximize Riesz energy. Or if you prefer, the regular polygon, quite surprisingly, is not optimal in the non-local polygonal isoperimetric inequality. So let me try to explain why this phenomenon occurs and where the relationship between the problem of maximizing Riesz energy and this problem which defines the critical radius comes from. So look at this critical radius. This critical radius is equal to the minimum of the diameter of omega when omega varies in the class of polygons with given area and given number of sides. So how is this problem related to our maximization of the Riesz energy? Well, the relation comes very directly from the definition of Riesz energy itself. So look at Riesz energy and consider the case we are dealing with when h is the characteristic function of a ball. Well, from the very definition of JR, you see that if I consider a set of diameter less than or equal to r, when I compute the characteristic function at difference x minus y, when x and y are in omega, if the diameter of omega is less than or equal to r, this characteristic function computed at x minus y will be always equal to 1. And therefore, the value of this energy will be simply equal to the double integral over omega times omega of 1, which gives me the square of the measure of omega, so pi squared. Whereas if you take a set omega which has diameters strictly larger than r, well, for such a set, this characteristic function will be 0 somewhere, which means that my Riesz energy will be strictly smaller than pi squared. And so if we take this fact into account, and we take now n larger than or equal to 6 even, we may observe that this r2, this minimum diameter, is not attained at the regular n-gon. This fact is a classical result due to Reinhardt, dating back to 1 century ago, more or less. In other terms, whenever n is even larger than or equal to 6, there exists another polygon omega sharp, which is not the regular one, like denoted by omega star, such that r2, this minimum diameter, is attained at omega sharp, and it is strictly smaller than the diameter of omega star. Therefore, if I take a radius r, which is above r2 and below the diameter of omega star of the regular n-gon, for every r in this range, when I compute the energy of omega sharp, applying this argument, I get that the energy of omega sharp is equal to pi squared, while since the diameter of omega star is strictly larger than my radius r, the energy of omega star is strictly less than pi squared. As you can see, this inequality tells you that omega star is not optimal. So in other words, as you can see, the proof is simple, is very direct, is a very direct consequence of this result by Reinhardt, which tells that the regular n-gon is not a solution of this minimum diameter problem. So if you have never met this problem before, you may be curious to learn more about these polygons which minimize the diameter under an area constraint. So I've added just one slide about these polygons. They are also called the largest small polygons because equivalently, they may be seen as polygons which maximize the area at fixed diameter. And so if we start from the first interesting case, which is the case n equal to 6, well, in this case, the optimal hexagon omega sharp was found by Gram. And in fact, it is usually called Gram hexagon. And its diameter at fixed area is strictly smaller, slightly smaller than the diameter of the regular hexagon. Or equivalently, if you prefer to fix the diameter, the area of Gram hexagon Hg is slightly larger than the area of the regular hexagon. You can see represented in this picture on the left, the gram hexagon of the same diameter as the regular hexagon that you see here. So this hexagon on the left has a slightly larger area. And what you see represented in red is the so-called skeleton, that is to say the collection of points which join two vertices at distance equal to the diameter. And in case of gram hexagon, this skeleton is given by a star plus a segment. While in case of the regular hexagon, it is given by an asterisk. And quite amazingly, this problem, this apparently elementary problem, is open for a number of sites strictly larger than 6 even. The determination of an optimal polygon is open. These are some papers in discrete geometry about this problem. In particular, some accurate numerical computations have been done in the case of octagons, and it is also known that the regular polygon is optimal, but only in the restricted class of polygons with a given number of sides. And so now, if we go back to our Riesz inequality, the fact that we have symmetry breaking for characteristic kernels of switchable radii implies very easily by approximation that symmetry breaking occurs also for other kernels. So still working with n even larger than or equal to 6, we can prove that symmetry breaking occurs also for smooth kernels, which are close enough to characteristic kernels if you choose the radius r such that symmetry breaking occurs for such characteristic kernel. In a similar way, if we work with power type kernels, when k is large enough, again, for n even larger than or equal to 6, symmetry breaking occurs. We can also give estimates, very rough estimates, about the k for which this phenomenon occurs. For instance, for n equal to 6, this occurs for k bigger than 2,800 and something. And so what is the moral, what is the conclusion of our results? Well, the conclusion is that for Riesz inequality, symmetry or symmetry breaking may occur independent of the kernel, depending on the kernel. And so the question becomes to understand for which kernel symmetry holds and for which kernel symmetry fails. And so here you can see a list of open questions which are related to the choice of the kernel. So for characteristic kernels, we have proved that symmetry holds below a certain threshold per prime, and symmetry breaking occurs above another threshold per second. So the question becomes determine the radius, or at least estimate the radius, the critical radius below which we have symmetry. In a similar way, for power type kernels, we have proved symmetry for power 2 and power 4, and symmetry breaking for sufficiently high k. So the question becomes determine the sharp exponent below which we have symmetry, or at least to estimate it. But for general kernels, well, for general kernels, the question becomes what is the property of the kernel, or what are the properties of the kernel which give symmetry for every n? And in particular, it would be interesting to understand whether symmetry holds true for the Hit kernel in view of its importance also in the relationship with Pauli and Zigo conjecture. And so in the paper with Beniamin and Dorin, we started the investigation in this direction by looking at the local optimality of the regular n-gon. And we looked at the local optimality of the regular n-gon by computing numerically the shape Hessian of the Riesz energy. And the shape Hessian can be computed as a 2n by 2n matrix, because a generic perturbation of a polygon can be viewed as a vector in R2n, because for each vertex you have a vector theta 1, theta 2, theta n. So theta I is a vector perturbation of each vertex. And so a generic perturbation which moves all the vertices can be written as a combination, as a sum of theta I, phi I, where phi I are piecewise affine functions associated with a triangulation, which are equal to 1 at a vertex, for instance, 1 here, 0 at the other vertices, and 0 also at an interior node. So since a generic perturbation is a vector in R2n, the Hessian matrix of Riesz energy will be a 2n by 2n matrix. So here you can see the entries of the shape Hessian of Riesz energy. These are the entries. As you can see, they're written in terms of H, of the first and second order derivatives of H, and also you may see appear the fine functions phi I and their gradient. These are the functions phi I which appear here in the perturbation of my polygon. And so this kind of computations, this formalism is very similar to the one used by Loren, who firstly computed the shape Hessian in case of lambda 1, and this kind of approach was also used in a relevant paper by Beniamin and Dorin, where they proved that the poly and zygo conjecture can be reduced to a finite number of certified numerical computations. And so using this expression of the shape Hessian, we studied the local optimality of the regular n-gon. First, for power type kernels. And in this case, the functional is homogeneous under scaling. So the volume constraint can be incorporated in the functional by multiplying the functional by the good power, so to get scaling invariant for this function. So we could compute the shape Hessian of this new functional using the shape Hessian of the shape Hessian of Riesz energy, and also the shape Hessian of volume. And we found that, as expected, the Hessian matrix of this functional under vertices displacement has a certain number of 0 eigenvalues. This was expected because my functional is invariant under rigid motions. So translations, rotation, and multiplies give 4 0 eigenvalues. And we found that the remaining 2n minus 4 eigenvalues are strictly positive, which means that the regular n-gon is a local minimum. And this computation, these numerical computations were done for a number of sites going from 5 to 10, and for all k even less than or equal to 24, which means that up to this value of k, for these values of n, the regular polygon is actually a local minimum. And then we looked also at the case of the heat kernel. And since the heat kernel is no longer homogeneous under scaling, to reduce ourselves back to a polygonal setting, we replaced this kernel by the truncation of its series expansion. For q equal to 12, this series is already quite close to the original kernel. So again, we considered the Riesz energy, and this time we had to introduce a Lagrange multiplier, since we don't have any longer homogeneity under dilations. And so we computed the Hessian matrix of this new functional, in this case on the space orthogonal to the gradient of the other functional, which is of dimension 2n minus 1. And in this space, we found again 3 0 eigenvalues, corresponding again to translation and rotations, no more to homodities. And the other 2n minus 4 eigenvalues were, as expected, strictly negative, confirming the expectation that in this case, since we have a decreasing kernel, the regular polygon is a local maximum. And the computations were done also in this case for n number of sites going from 5 to 10, and for some values of t, of the parameter t, going from 1 to 100. And actually, we observed that there is monotonicity in t of the eigenvalues, so we think that the result holds for all t in this range. And in fact, we suspect at least that the regular polygon should be optimal for the heat kernel for every n, including n even larger than or equal to 6. But we don't have a proof by the moment of this fact. So stop here, and thank you a lot for your attention.
Thanks a lot, Ilaria, for this very nice talk. It's now time for questions, so you can either just unmute yourself or ask the questions in chat, and we will transmit them.
Okay.
I'll start. I'll start with a question of my own. So the this theorem that gives you as an open problem, what is the optimal polygon for n greater than 6? I mean, so this open problem. Do we have any idea if for n large, we expect this optimal polygon to converge to something like, for example, should it be not the regular polygon, but maybe close to a circle, or do we know that it should stay away from looking like a circle?
I guess that for n large, it should converge to a circle because because of the continuous version of the inequality. I don't expect that it should be asymptotically different from a circle for n large.
Okay.
Because if you look at this problem, the problem which defines our critical radius, this problem in the continuous case, this problem is solved by the ball. And so this is a classical inequality. So I expect that the optimal polygon should converge to a circle.
I think it could be interesting to look at for n large again how far from the circle it can be. Would give a good if this can be quantitative, it would give a good range for where to look for these
It's an amazing problem. It is related to the shape of the shape of this optimal of the largest small polygons is related to low polygons. You know, low polygons are polygons, generalized polygons in which whose boundary is made by a finite arcs or finite number of arcs of circle and constant width. So the shape is somehow related to the shape of these low polygons. This is where the difference from the case and odd and even comes from.
Thanks. Do we have other questions for Ilaria? Yes, Rajesh, I see you unmuted yourself if you want to ask a question.
Yeah, hi, Ilaria.
Hi.
So just wanted to know, so when you were talking about the Hardy-Littlewood inequality, and so you were showing some construction on page 12 or something, I guess, of your book. So I had this question, meaning, would it is it probably not true that you for this inequality you always have a convex polygon as a solution, and some of the convexification thing might work? I'm not sure if it's.
In fact, a posteriori, yes, because a posteriori an optimal polygon is convex.
Yeah.
But the construction gives you a star-shaped polygon, not necessarily a convex one. Then once you know it is a star-shaped, you are free to exploit optimality conditions, and the optimality condition give you directly the regular polygon. So somehow we don't pass from the class of convex polygons.
Yeah, another question, meaning so for many of these inequalities, meaning most times when you have let's take probably the case where the optimal thing is a regular polygon, which meaning if you are below the Steiner, I mean before the below the symmetry breaking. So how meaning I didn't understand so much because may have to read your papers, but meaning the advantage of working with the optimality condition and shape derivative versus just trying to use the equality case in Braskamp, Lieb, Luttinger. Is it possible to just apply equality case in some of these situations, and meaning the equality of the in Braskamp, Lieb, Luttinger to?
You mean you would like to exploit the equality cases in Braskamp, Lieb to get the uniqueness of critical polygons?
Yeah.
No, I don't think so, because critical polygons a priori is not a maximizer of Riesz energy. It is simply a critical set. So I mean, a maximizer is a critical set, but the vice versa is not necessarily true. So if you start with something which a priori is only critical, you cannot exploit the optimality, the uniqueness of the maximizer, because a priori a critical polygon might.
Yeah, I understand, but when you're dealing with the inequality, the Hardy-Littlewood type of inequality, then you are looking for a maximizer or minimizer, not just a critical polygon. So
okay, so you say when I try to solve this one, okay, and
or the characteristic version for the I mean, you had this the ball, the characteristic potential, or I don't know how you called it, but in the other inequality, the Riesz kind of inequality. Yeah.
I don't understand what you would like to do. You would like to use.
Yeah.
How can you use Hardy-Littlewood for arbitrary kernels? Because for power 2 we can develop and reduce the Riesz type energy to Hardy-Littlewood 1. But for an arbitrary kernel, how can you reduce back Riesz to Hardy-Littlewood? I don't know.
Oh yeah. Okay.
This is a specific, somehow specific chance of the power 2. Because of this simplification, because somehow one of the two variables is scaled here at this level, but otherwise for an arbitrary kernel, I don't see any way to pass to reduce a Riesz type inequality to a Hardy-Littlewood 1. Say.
Yeah, probably it was not my question. I think probably I didn't state my question so clearly, but yeah, I got your point.
Anyhow, feel free to contact me later or write me back. If you...
Thanks a lot, Rajesh, for the question. Do we have other questions for the speaker? Muhammadu, did you want to ask a question? Okay, it seems like we have exhausted the questions. Thanks again, Ilaria, for this beautiful talk today, and we will reconvene next week.
Thanks everybody for coming.
Yeah.
And
we will reconvene next week with a talk by Luc Ilaria, who will tell us about spectral tools for geometric degeneration. So see you all next week.
Thank you very much. Bye-bye.
Thanks a lot. Thanks everybody. Bye.
Sorry, about slide 9.
Slide 9.
Oh, okay. There was one
here, no problem.
I have no problem about connection. Yes, here. My question is about the perturbation of omega epsilon.
No, I cannot hear you very well. Speak more slowly, please.
Okay. If I saw this, I think about derivative of about shape derivative or topological derivative like Bucur or Delfour problems, and I think that we will have some perturbation.
No, I don't understand. I don't understand. Can you write in the chat? Because I cannot understand the English very well.
Can we have some holes? Some perturbation like make holes?
Don't understand.
Okay.
Maybe if you want to write down your question or to send your questions in writing.
Yes. If you're willing to, please write the question in chat so that it is easier to. The weighted Riesz energy. What do you mean? Weighted Riesz energy. I'm sorry, I didn't understand your English. The weighted Riesz energy. I don't know if I give a correct interpretation to your question. Maybe you mean a more general version of Riesz type inequality in which you also have a function, because the most general version of Riesz type inequality is not this one, right? This is a very special case of Riesz inequality in general, the Riesz inequality that you find in all that was proved actually by Riesz involves three functions. Yeah? You integrate f, integrate over Rd, f times g star h, right? And this is the version of Riesz inequality in which two of the three functions, if you write the integral of f times g star h, here both f and g are taken equal to the characteristic function of a ball. And so here you have f star and g star. In the general Riesz inequality, the integral of f times g star h is less than or equal to the same integral where you replace f by f star, g by g star, and h by h star. So you're right that this is a particular case in which both f and g are equal to the characteristic function of omega. It is true that it would be interesting, well, it could be interesting to look at what happens when one among the two functions is the characteristic function of omega and the other two is in arbitrary kernel, but we didn't investigate this more general version. So summing up, I don't know if these more general versions you're looking for are true or not. Rather than weighted Riesz energy, I would say the more general form of Riesz inequality, because it is not a weighted Riesz inequality, it is the Riesz inequality in a more general form. I guess it should be even more difficult, of course, that case, but we didn't look at that more general inequality.
I guess you would still have to hope for some form of symmetry in the kernels if you want if you want for this symmetry breaking to be
yes,
relevant.
But already it would be more general, even if if you take f no, of course with the kernel with the kernel which is not even symmetric, it should become no, I mean with another function, I mean, or perhaps this was the question, with another function replacing somehow a characteristic function of omega here with another function which is a priori radial, and we looked at what happens. It seems to me that the problem makes sense, but we didn't look at it. Was that your question? Oh, nothing.
Yeah, well, it seems
so
like
much, I was not so much helpful, but it's an interesting problem.
Yeah, I mean, it's what I find with these shape optimization problems, right, is that it's hard to we can always add an extra complication to the problem, right? We can always add a more general kernel, a more general object and everything, but then it becomes by doing that somehow we do more general, but we remove some of the original interest, right?
Yes, that's exactly the point. Here, changing the kernel is not a technical point. It seems to be quite surprisingly. To say, if I catch it, in the sense that usually changing the kernel may produce somehow generalization or technical difficulties or. Here, the point seems to be the kernel.
And it's amazing. I really.
And it's amazing. And the point is that we don't have understood the point in the sense that we don't have understood why for certain kernels does it work, and for other kernels it doesn't work. For characteristic kernels, the size of course is the point. But if you take a kernel, an arbitrary kernel,
it's interesting also how you have this. I mean, these power kernels. There seems to be a clear side. On one side, you get the symmetry breaking. On the other side, if the power is not big enough, and for the exponential kernel, if I'm correct, for the exponential kernel, you also don't expect symmetry breaking, right?
We expect, but I have to say.
You expect symmetry breaking or no symmetry breaking for exponential
We
kernel?
expect symmetry for the
Yes.
heat kernel.
It would be interesting. I mean, that's more of a like a dream theorem, right? But to have to have it in terms of just having some explicit decay condition. And on one side of this decay, we have symmetry breaking. On the other side, we don't. And maybe if you decay but not fast
Yes, it
enough.
might be. It might be the decay, but don't know if it is the speed of decay, some joint with some concavity or log concavity.
But decay in some Sobolev norm is what I have in mind, because this the characteristic function, I mean, sure, it decays in the sense that it's
it goes abruptly to zero.
Yeah, but in Sobolev norm, it's very singular, right? So and maybe that's the kind of thing that OE analytic methods might be able to see, because they see these decays very the Sobolev norms really well. I don't know, you know, I haven't thought about the problem a lot. It's just what came to mind when seeing this.
Yes, but it's intriguing because this symmetry breaking was somehow a big surprise, at least for us.
Yeah, I mean, I do find it surprising too. And it's a really interesting. Okay, I probably need to go. It's the end of
okay.
the day, but thanks a lot for the talk. It was super interesting.
Thanks for the invitation again. It was a pleasure.